Thank you very much for inviting me. Very happy to be here. Long horizon agents are clearly one of the frontiers of AI research right now. If I look at my Codex session, my median usage is around 10 minutes. If I look at the mean, it's around 20. Why is it not more? Why agents are not working for me for a longer time? I think it's a very worthwhile question to be asking today for AI researchers. But to start with, let's start with the obvious, which is we already live in the era of agents. Agents are here, but we are very early in this era. In my mind, O3 was the first really agentic model, and that model was only released in April last year. So we are just barely more than a year in the era of agents. That means the models are very early. They have improved vastly since O3, but at the same time, there's much more improvements to be had. The products are improving, the adoption is coming. A lot of things are still not figured out. And we live in those beautiful times and that beautiful opportunity to figure those things out for the future decades of agent proliferation. Even thinking about the definition, what makes agent an agent? I think agent is a very fuzzy term that is hard to fully define what it is. For me, I put some pieces that I think make an agent, which is agents use tools, because agents should be able to act on my behalf. Agents are most likely async. I tell agent something to do, and it goes on and does its work. Agents are usually goal-oriented, which you specify something high-level, what you want the agent to do, and the agent fills in the blanks. And agents are working usually over long horizons of time. You don't do back and forth every 5 minutes. You let agent do its work for extended periods of time. And whenever we extend the length of the time that the agents are working, there is this pretty obvious observation that with every step, the neural networks that we train are probabilistic. They make failures. So with every step, there is an exponentially growing through the length of your trajectory chance that something goes wrong. And that was a very big reason why we couldn't have agents for many years until very recently, because the neural networks were getting off the rails. And this is pretty classical assumption from the reinforcement learning literature. And why do we need actually reinforcement learning? And the moment happened when me and my team were able to scale reinforcement learning to larger and larger amounts of compute, where we finally found a recipe that allowed us to train models to recover from their own mistakes, train on their own trajectories, and that suddenly started making the models be able to succeed in harder and harder tasks. And what did we see? The first thing is obvious, the more compute you spend, you could see proportionally on a logarithmic plot the capabilities of the models improving. But we have also seen the other thing, which is one of the most important shifts in machine learning of the recent years, which is the more the model thinks, the more tokens it spends on a task, its performance improves. So not only the models trained with reinforcement learning were not falling on the trap of exponentially increasing the chance of failure on a trajectory, they were able to recover from that, but they were able to even keep productively thinking for longer and longer. So essentially, the longer your trajectory, the better the results you are getting. We entered the test time compute era and token maxing. So then we have this now. This is a plot a lot of people thinking about agents are very familiar. It's a plot for how long agents can work from us. And since we started scaling reinforcement learning, it reaches new heights with the latest readouts of around 12 hours, 16 hours for some of the best frontier models of the day today. So the question is, maybe this is it. Maybe we have reinforcement learning, it works, we can throw a lot of money at it, and maybe we just keep scaling and we'll have agents working for whatever amount of time we would like. Is that the case? Is that the solution? Unfortunately, there are problems. There are challenges. I don't think we are done yet. The first problem, which is that the economics is here kind of unfavorable in many ways. To sample a trajectory of length n, generally your cost is proportional to the length of trajectory. If a quadratic attention is even slightly bigger. But let's think for a second linearly that the cost of each token is fixed. So to sample a trajectory of n tokens is proportional to the length of it. But also how our today's reinforcement learning algorithms work, they assign single reward for that trajectory, which is there aren't really any in modern RL credit assignment methods to assign that reward to any specific tokens, which means you get one reward to the trajectory of n tokens, which the information per token you are getting is roughly 1 divided by n. And the cost of that trajectory is also n, which means that your learning signal decays quadratically in the length of your trajectory on the horizon you are doing. Which is if it would be linear, it would be like pretty okay to keep throwing more money, and we know if we want to train agents to work twice as hard for twice longer time, we need to spend twice more money. That's a pretty reasonable thing, but if it's quadratic, it is becoming pretty brutal. The big labs today are very good at spending a lot of money training models, but the quadratic cost makes the scaling of that considerably harder than it would seem at first sight. The second bit, which is even harder, is latency, because as much as there's more and more investment coming to the AI world nowadays, no one has time. There isn't that much time, and the latency problem comes from the following. Imagine you have to sample a 12-hour trajectory of an agent. It takes 12 hours to sample it. And then you take a gradient step to update your model to reinforce the successful trajectories. And then you have updated weights, and then you sample another 12-hour trajectory. You are able to do full 2 gradient steps in a day of your reinforcement learning agent. That means roughly 14 gradient steps a week. That means like 60 gradient steps a month. It is not a very fast training method, and no one has time in today's world. So training for very long trajectories and for long horizon thinking is meaningfully very, very hard, harder than many realize. And all of the progress in the field, and the reason we have even any agents that can think for a long time, is usually we put some kind of harness on top of it, because the agents are very good at doing short horizon things, short horizon tasks. And the truth is, a lot of long horizon work can be glued very successfully together from doing smaller and smaller things. And we have these things called /goal in Codex and Cloud Code, which is very powerful. We just create a fixed goal for a model. It runs for however long it can, then it revisits itself, and it continues to do that. We have plan mode. We have many ways. We have sub agents. There are various ways that are not native to the model. They are not backpropagated through. They are not trained, but to utilize the model's ability to work on shorter term goals and structure from them being able to spend more and more. They are very successful, but the history of machine learning has always been that whatever we can backpropagate through wins with things that we cannot. Everyone's probably pretty familiar with auto research and what auto research means. And the story of almost every auto research rollout is you get a lot of progress pretty early, but if you go further and further along, it kind of stalls, it kind of stops. I haven't seen yet today with today's models any particularly successful auto research rollout. I think research is one of those tasks that is inherently hard, serial, and long horizon. And today's models, it's not very easy to glue it from a small horizon thinking to think about larger scale research projects, and auto research is one of the places where we can definitely see it. So a lot of the questions like I am asking myself is, how did humans master pursuing long horizon goals? Very famously, Andrew Wiles spent 7 years working on a single goal of proving Fermat's last theorem. He was successful. It was a seven-year project. How do we train our models to do 7-year projects? And thinking about humans even more, like I've asked ChatGPT, at which moment did humans start developing long-term planning? And what ChatGPT has told me, that we have until today roughly 10,000 generations of humans since the moment we were able to since the moment we were able to start doing any significant long-term planning. Since that time, there was roughly 120 billion people. So maybe this is it. Maybe we need 10,000 gradient steps and 120 trajectories to sample, and maybe that is what allows us to optimize for long-term, long horizon planning as well as humans do. Also, gradient descent is more sample efficient than evolution, so maybe we have even more, and that's something for us to think about and revisit. The value functions as a research direction is one thing that definitely can help. It's if we got good value functions for AI research, it will be extremely helpful. I think the research on value function has been, like, at some moment we basically threw out value functions when doing reinforcement learning on large language models, and everyone has seen that it works as well. Value functions are very, very hard problem. I have some amount of skepticism in how much progress we can do on really good value functions. Very often finding good value function is much harder than solving the problem we are trying to solve. But if someone figures out value functions, we're good. We can solve as long horizon problems as we would like. Maybe continual learning is the answer. Continual learning tries to solve this problem from the other side. We try to update the model for the loop. If we have long horizon 7-year loop, let's prove this theorem, and we repeat the same thing every day, but we don't repeat it with the same model, because the model updates on the new data. Every day the model learns something, the model improves, and the model gets better. I think continual learning would be able to get us through that very, very well. The question is how. And this is an unsolved problem. This is a problem that is worth solving. And if someone is looking for what do we want to work on right now, right here in this age of machine learning, I think long horizon agents is absolutely one of the valid choices. When we get that technology, we will be able to put agent towards working on hard research problems. We'll be able to have them to run companies. This is a very long horizon task that is very, very economically valuable. And if I want to delegate to an agent, I don't want to be telling it what to do every 30 minutes. I want to be able to act on my behalf for a long periods of time. And I think this is extremely valuable. So the research is not done. There's much work to do. And the objective is agents that can keep going for us and keep getting better over time. Thank you very much.